it's time. And welcome everybody to the Israeli Vacuum Society meeting, to the session of Nanoelectronics and Spintronics. We have 6 speakers today. We have a roundtable discussion of the future of electronics that will follow the talks. So it is my pleasure to announce our first speaker, Andras Kiss from EPFL, Switzerland. He will be talking about electronic devices in 2D materials, right?
Yes. Yes. Okay. So I will show our latest work in that direction. Okay, can I start?
Yes, please.
Hi. So thank you very much. It's nice to see you, and I would also like to thank the organizers for inviting me and giving me this opportunity to present our work and honoring me with the keynote talk here. So I'm going to be talking about our recent work in the direction of using 2D semiconductors such as MOS2 in electronic devices. So the 2D materials such as transition metal dichalcogenides are the main, let's say, the main topic of my research work, and this is a family of materials with something like 40 stable compounds, which are sharing the common structure in which transition metal atoms are strongly bound in 2D layers with chalcogenide atoms, and these layers are weakly stacked in a vertical direction via van der Waals interaction. So this is similar, somewhat like the situation you have with graphite and graphene, and you can extract single layers out of these bulk crystals and use them to make mesoscopic devices. Now, depending on the metals you have in the structure, you can cover a broad range of electrical properties, from semiconductors, semi-metals to superconductors or metals. And most of my work is focused on the semiconducting variety, since this is probably where practical applications, at least in the context of electronics, are expected to come in the, hopefully in future. And so my group is working on several different intertwined topics based on that cover a wide range of projects on 2D materials. In one set of projects, we're working on so-called classical semiconductor devices, where we're trying to make more and more advanced transistor-like devices and circuits. These, in principle, could also be done using other types of semiconductors, but 2D semiconductors bring some advantages in terms of performance and power dissipation primarily. Then we're also trying to develop new device concepts which are based on some unique properties of 2D materials, and we have a strong activity in the growth, where we operate several home-built and commercial MOCVD, CVD, and an MBE system for growth of transition metal dichalcogenides and heterostructures. Now, in this direction of semiconductor devices, pretty much the work is motivated by a problem which is related to heat dissipation in electronics. And this problem is, I think, very nicely illustrated on this picture, where you have a student removed a heatsink from a processor, and then he replaced it with an aluminum pan. And by playing games, he could actually reach temperatures over 100 degrees centigrade, which are enough to cook food. And something like 10 years ago, when I found this picture, it was one of the first of this kind. Now you have actually an entire YouTube channel dedicated to people cooking different kinds of food in computers. So this is kind of funny, but it underlines a much more serious problem, and that's that the IT sector itself is consuming larger and larger amounts of energy, and which is, of course, also mirrored in the emission of CO2. And there is a lot of talk already in cutting plane travel. Well, this was at least a topic before the pandemic. So this is still pre-pandemic. There were these predictions that this sort of a conscience and environmental consciousness could decrease flight air traffic a lot. But as far as the ICT sector goes, it's pretty much consuming and emitting roughly in the same level as the aviation sector, but there is for now, still much less talk of it, but I'm convinced that this is something that's going to come up very, very soon. And some pessimistic projections, which actually have accelerated because a lot of activities have moved online recently, I predicted that by 2030, the ICT sector would consume 1/5 of electricity wherever that's produced, and the data centers alone would consume something like 7% of all electricity. So this is obviously becoming a more and more pressing environmental issue. Now, some of these electricity is obviously coming from the production itself, but a lot of it is spent on several levels in electronic devices, circuits, servers, computers, and these can be related to several sources. So the first is coming from the fact that transistors, which are one of the building blocks of electronics, are becoming less and less efficient. They are dissipating energy as we're shrinking them down. So the so-called leakage currents become more and more dramatic. And these leakage currents are coming from the fact that if you make a field effect transistor in this simplified geometry and you try to apply an electric field to switch it off via the gate electrode, then the electrostatic potential, which should prevent the electrons and holes from tunneling between the source and the drain electrode when the transistor is off, this electrostatic potential becomes more less well-defined and more blurred because the sizes of the structure are becoming smaller and smaller. So in order to make a transistor that you can efficiently switch off, if you want to scale the length, you also have to scale the thickness. And this is where using 2D materials, such as, for example, molybdenum disulfide, becomes a very good choice eventually, because it allows you to shrink this critical length for making a transistor by just taking a thinner material. And here using 2D materials brings several advantages. So it allows you to shrink the length of the transistor by shrinking the thickness of the semiconducting material, but it also allows you to relax a little bit the requirements, for example, on this gate dielectric by allowing you to have a slightly thicker gate dielectric and still have the same type of a switching performance. And this is where we made some important first steps already 10 years ago, where we made the first transistors based on molybdenum disulfide, which was the first example of using a 2D semiconductor in the context of electronic devices. And it showed that indeed there are some possible advantages to using 2D materials such as MOS2 in this direction. So now if we want to figure out what are the sort of performance and what are the limits, theoretical limits for the power dissipation that we could have in a single transistor-like device and how far we can actually go by scaling, and we need to look at the Landauer limit, which for a transistor-like device, for a charge-based switch, it basically tells you that the minimum energy that you need to dissipate simply from thermodynamic point of view is 4 times the Landauer limit, which is the basic limit that comes from the fact that if you switch a transistor and you don't keep track of its state, then you're erasing information and you're increasing the entropy of the universe. So now if you look at the different types of transistors and the lengths, gate length, and how the switching energy was scaling with time, we can see that this would be the theoretical limit for transistor-like devices. We are pretty much following very nicely an exponential decrease in dissipated power, but we're still 1 to 2 orders of magnitude away from the Landauer limit. So there is, of course, still advantages to be gained by shrinking the gate size and by which is, of course, expected to be facilitated or enabled by using 2D semiconductors. But there is another part where a lot of energy is wasted, and that's actually much more pronounced than than if you look at just a single transistor. And that becomes obvious if you start to look at a whole computing system, for example, a computer or a processor, and then you see and compare the power dissipation with the Landauer limit. So if you take a relatively high-end processor from a couple of years ago, and the numbers haven't really improved dramatically in the meantime, and if you look at some benchmark and how much this processor is dissipating while achieving some performance level, and you just try to calculate in a very back of the envelope type of calculation what is the dissipated power per operation, you're getting that we are something like 10 to, so basically 1 billion times worse than the Landover limit on the level of an entire system. And this is extremely wasteful, of course. And now where is this extra waste of energy coming from? It's coming from the von Neumann architecture that we're still using in most of computers today, where the basic idea that was introduced by John von Neumann, and it was also followed, was to separate the CPU and the logic operations which are performed in a CPU in one discrete physical unit from the memory, which is where you store the data, which would be another physically separate entity. And then if you need to perform calculations, you need to get the data back and forth between the memory and the CPU. And of course, this movement of data is reflected in currents, voltages that have to be changed in the device lines that need to be charged. So there is, of course, power dissipation, which is followed from this. Now, back in the days of John von Neumann, of course, this was necessary because it was not really possible to realize the same type of a device, both the CPU and the memory using the same type of a device. So you had to physically separate it. But something like 10, 20 years ago, this has started to become a possibility. So there is an idea to implement logic operations using different types of memory elements. And if you can use the same type of a device to perform both logic operations and data storage, then in principle, you could intertwine them and co-localize both memory and logic, and then save some energy on this movement of data back and forth. And there are several different types of technologies that have been nicely reviewed in this review paper, and several different types of devices that you could use both as a memory and the logic. And when we did some review of this data and numbers, we realized that one which is relatively useful and is also very close to us are the flash memories and flash memory elements. So back in the early days of 2D devices, we realized the first flash memory elements based on MOS2, and it was showed that in principle you could make both transistors and memory elements using the same materials. So thinking more about this, we decided to refresh a little bit the design and try to make these devices in a more scalable way. So the first approach was to use, instead of exfoliated material, MOCVD grown material based on the chemical reaction between carbonyls and H2S, where in principle you can grow very large grain size, high quality semiconducting 2D materials. In principle, you can also do this on a wafer scale. So we have been able to do that for quite some time now. And then we integrate these high quality materials onto structures that are prefabricated on the wafer scale, where we have gate electrodes, which we use to control and switch the transistor devices. But in addition, we also have floating gate structures. So these are very thin metallic films in which charge can be stored, and then this stored charge can influence the conductivity of the 2D film. So because we can make these semiconductors on a wafer scale, we can in principle make relatively complicated structures. So this is an example of a small circuit with 8 of these transistor elements. And if you look at the cross section of the devices, we can see that we can very nicely and very reliably, due to this process where we have first everything done on the wafer scale and then we transfer the 2D semiconductor on top. Because of this, we can very reliably make a lot of these elements in parallel. So now the memory effect and the storage of data can be seen if we sweep this gate voltage and we look at the current in the device. So then we get this hysteresis, which is coming from the fact that your charges, depending on the voltage configuration, can be stored or released from this floating gate, and that influences the threshold voltage of the transistors. And then if we perform just the basic characterization of these memory elements, we see that we can in principle extrapolate to something on the order of 10-year retention for 2 memory states. and the devices themselves can survive at least 10,000 cycles of switching and erasing. And yes, and if we now look at the variability of these devices, we can see that they are actually very highly reproducible. So now this memory effect, the interesting thing is that it's based on the idea that depending on the gate voltage that we apply to the transistor, we can store charges on the floating gate or we can release them. And this is how the basic memory effect functions. But this can also be used in a more analogous way. And instead of looking at this as a programming and erasing of memory, we can actually vary the amount of charges which is stored on this floating gate to program different conductivity levels into our device. So with this, we can use the memory effect both to store the data and to also program the transistor itself. And depending on the amount of charge stored on the floating gate, we can have a fully off transistor, a fully on transistor permanently, which memorizes the state, and we can also modulate the conductivity in between these two different states. And we can also do that much more precisely. So we can basically set a desired conductivity level and then program it into our device. And now with this, we can actually turn our memory elements into logic devices and logic circuits. So we can take the same memory element, and then we can program it to be either fully off, fully on, or to behave just as a regular programmable transistor. And with this, then we can demonstrate logic operations, which work just the same way you would normally work with a transistor, except that now we use a memory element to do the logic operations. And furthermore, we can actually implement a so-called universal logic gate, where we can start off with a circuit composed of either 4 or 9 memory elements, depending on whether we want to have operations between 2 inputs or 3 inputs. And then using these different memory programming states, we can pre-program the circuit to behave as any kind of a logic circuit with the 2 inputs. So we can program the memories. They work for performing a certain logic operations. And then if we want to use the circuit for something else, we can reprogram the memories and use them for those other operations. So this is then a universal way of making electronic logic devices, where in principle you just start off with a single circuit, and then you can reprogram it as you need for different types of calculations. So this is a demonstration of using 3-input or using 2-input adders for performing summation of numbers. So to summarize, I would like to, we've shown how you can use these flash memories based on 2D semiconductors, and also for logic devices, reconfigurable circuits, and universal logic gates, which could allow you to use the same circuit to perform different types of calculations. And at this point, I would like to thank my group for the very hard work. Most of this work on logic devices was done by Guilherme Milhato Marega, who did the devices and came up with this idea of universal logic circuits, and Zhenyu Wang, who did the material growth. So if you have time, I would like to, of course, thank you for your attention and questions.
Thank you very much for a very exciting talk. And,
thank you.
We have about 1.5 minutes for questions. So if there's anyone who wants to ask a question, this is the time. Okay.
Talking about the Spintronics, would you think that adding the spin degree of freedom will add something to those kind of devices?
I mean, maybe, but that would be for us a bit complicated right now. But maybe you could have some kind of also in parallel memory and computation on the charge and the spin domain. But this is still somewhat more on a conceptual stage, I think.
Thanks.
Thank you.
Have you tried going in less traditional directions, like memoristas? Because
yes, so this is something we're close. Yes,
Yeah.
so this is something we've actually done. So we haven't published this yet, but it's something we actually try to do, and it seems to work actually quite well.
Mhm. Okay, so thank you very much for your talk, and now we move on to
Thank you.
next
It was nice
speaker.
seeing you. Hi, Harish.
Thank you.
Thank you very much, Andres, for joining our platform.
Thank you.
I really
Thank you.
appreciated that. Thank you.
Thank you very much. Okay, let me stop sharing. I just need to find the controls. Okay.
Okay. So, oh, sorry. And okay, Zev, you're now co-host. So one of the main motivations behind miniaturization was to reduce resistance to gain faster devices. An alternative approach has been to replace electrons with photons. And so it's my pleasure to introduce our second speaker today, Zev Zalewski of Bar-Ilan Engineering. Zev will talk about silicon photonic data processing devices. Zev, the stage is yours.
Yes, thank you very much. Thank you for the introduction and for inviting me to give this presentation. So indeed, I'm from Bar-Ilan University, and I'm going to speak how to use silicon in order to realize on silicon wafers photonic devices. Now, why is it a problem? The main problem is that silicon is very good for guiding photons, but because of its relatively low nonlinearities and relatively low electro-optical effects, it is very difficult to realize in silicon various photonic processing devices, such as logic gates, transistors, and so on. On the other hand, we want to use the advantages of photonics because of the capability of transmitting larger bandwidth, having lower power dissipation, having lower noise level, and also to allow photonic to work with microelectronic circuitry. So we want to use silicon, we want to use photonics, and the question is, how can we overcome the limitations that I have mentioned? And this will be the aim of my talk. I will try to show you some different non-conventional approaches to solve this, to allow integrating of photonic devices in silicon, photonic dynamic devices like transistors and logic gates. The outline of my talk will include the following topics. I will speak about integration of nanoparticles in order to realize hybrid photonic transistors. I will speak about electronic nanotransistors, about photoactivated logic gates and modulators. I will speak about plasmonic logic gates, enhanced photonic devices, multimode interference-based logic gates, cascading of photonic devices, and eventually at the end of my talk, if time will allow me, I will speak about photonic cyber related concepts. So as I said, it is possible to realize dynamic devices in silicon. So one way of doing it is a way of integrating nanoparticles into specially designed photonic devices. Let us assume that we have a device that is seen in this slide, in which we have a waveguide that guides photons. And then on the path of this waveguide, we generate a nanometric hole in which we place a charged metallic nanoparticle. Now, this charged metallic nanoparticle, when it is positioned in the lower part of this drilled hole, will not significantly affect the propagation, the guiding of the photonic radiation, as you can see in this simulation. So the radiation will be coupled to the output of this device. On the other hand, if we apply an external electrical field, because the metallic nanoparticle is charged, it will be shifted, even a shift of a few nanometers will cause scattering of the photons that are entering into this device, specifically if the plasmonic resonance of this metallic nanoparticle is matched to the wavelength of the guided photons. And then the efficiency of coupling light to the output of this device will be very low. So this is a modulator, a transistor that is based on the operability of this nanoparticle, but it is fully realized within silicon. Now, the question is how one can realize and fabricate such devices. So we have developed a, say, semi-mass production technique that uses microelectronic machinery to realize those devices. So we mark our silicon wafer with a FIB, which causes implantation of positive gallium ions in the silicon wafer, and then we put a solution with metallic, negatively charged surfactants, metallic nanoparticles, and those nanoparticles are attracted to the position where the positive gallium ions were implanted. And after we clean our wafer, the metallic nanoparticles stay only in the location that were marked with the focused ion beam. This is how we can bring our nanoparticle into the designed hole within which it needs to move. Now, if we want to build the full device, this is an example of the full device. So this is this photonic transistor. Those are the electrodes. This is a zoom in of the device. Those are the two electrodes. This is the hole within which we place the nanoparticle. And by applying electrical field, it is shifted here and changes the coupling efficiency of photons that are going from this waveguide to the second waveguide. You can see here some experimental results of inserting the nanoparticle into the hole. And in a second, I'm going to show you also how the nanoparticle moves in this hole. But before doing that, I want to say that this technique can be further extended, and not only for electro-optical modulator, in which we modulate photons, but the shift of the nanoparticle is done by applying electrical fields. We can also do it in an all-optical modulator in which we have the input. This is the input. This is where the nanoparticle is. And the shift of the nanoparticle is done by additional second photonic input that generates a photonic interference within this gap or hole that we have fabricated. And by changing the relative phase between those two inputs, the interference fringes move and they shift the nanoparticles with them due to the gradient forces, photonic forces. You can see here the fabrication of this device, and here you see some experimental results in which we shift the nanoparticle within this fabricated slit, along this fabricated slit, and through this we generate the desired modulation that once transmits light to the output or blocks the light coupled to the output. This concept can be further extended and realized in an all electronic manner, in which we fabricate 4 electrodes with small hole here between them. This is a zoom of the hole where the metallic nanoparticle is the charged metallic nanoparticle is placed. This is the source and the drain where the current of the information is passing. And those electrodes are the gate. By applying voltage here, the nanoparticle is moving within the hole and changes the electrical resistivity between the source and the drain. And this is how the modulation is performed. You can see here the device. By the way, if possible, to mute the other participants, it would be great because I hear a lot of noises in the background. Here you can see some experimental results. You can see, for instance, the blue line, which is the measurement of the resistivity between the source and the drain. This is the resistivity when the nanoparticle is shifted away from the source and the drain. The resistivity is high, about 8 gigaohm. And when it is shifted to be positioned between the source and the drain, the resistivity is significantly lower, 120 kilo ohm. So this is a nanometric transistor. The same concept we have also applied to realize optical switches, in which the shift of the position of the nanoparticle changed the coupling of the input beam to the 2 possible photonic waveguides positioned in the output. So it's like switch, not only a transistor. Another concept that we have been working on is what we call photoactivated modulators. They are built like this. This is how the device is built. The device, in this device, the information is electronic going between the source and the drain, and the photons are used as the gate control, the command that closes or opens the channel between the source and the drain. So this is an oxide barrier. And in regular situation, when the illumination is off, the channel data is open. The p-type region, this yellow region, is in deep depletion, and most of it is outside of the channel through which the information should go, so it is open. When we illuminate with light, the p-type region is becoming in the state of inversion, and the depletion region goes into the channel, blocks the channel of the information between the source and the drain, and the resistivity is high, no current is going through. So we have fabricated such chips between any two points here, connectors here, we have such a transistor, and this is the channel through which we do the illumination. And you can see here the operation. So the yellow line is the illumination, the green line is the green, and the blue is our output. So when the illumination is on, the output is high, and when the illumination is off, the output channel is low. Okay, and then by properly wiring this device, we also realize different logic gates like NOR gate and NAND gate, and here you can see the image of the fabricated chip and its operability as logic gate. Another topic or direction we're investigated is plasmonic logic gates. We have developed special antennas that efficiently convert light into plasmons, and by properly connecting those antennas and generating special plasmonic waveguides, we could realize a plasmonic XOR gate. You can see here the measurement. After a propagation of approximately 150 nanometers, we have a modulation of the output in approximately 15 dB extinction ratio. We also try to enhance the effects that you inherently, the nonlinear effect that you inherently have in silicon. The inherent effect is the plasma dispersion effect. To enhance the effect, to allow smaller modulation voltages that will still allow a strong modulation of the photonic information guided through the photonic waveguide. In order to do that, for instance, we fabricate electrodes which are not conventional electrodes, but they have a Bragg structure. And by that, when we apply voltage on those electrodes, due to the plasma dispersion effect in silicon, we generate a periodic change in refraction index, which affect stronger the information photons. Another direction of enhanced devices that allow us to realize logic gates and transistors in silicon is done when we try to implant quantum dots into silicon wafer and use the nonlinearity of stimulated absorption occurring in those quantum dots in order to realize logic gates. In this case, this is a chip in which we experimentally realized logic NOR functionality. It is very simple to realize various interference devices within silicon, and we have designed various waveguides, interference waveguides, what is called MMI, multi-mode interference modules, that could realize various logic operations, Boolean operations like AND, OR, and so on. And we even tested it experimentally. But what is the problem? The problem is that interference is a linear operation. So if we realize one logic gate, then it's fine, because at the output of the logic gate, we have a detector, and the detector erases the phase, it captures the intensity. But in processing circuits, we need to have a large fan out. We need to cascade many logic gates one after the other, and not a single logic gate. And as I said before, the main problem of silicon is its low nonlinear effects and its low electro-optical effect. So how can we use how can we use linear devices realized in silicon in order to realize nonlinear processing like cascaded Boolean logic gates. So we have developed a novel approach for cascading logic gates, which are realized via linear devices. And what we do is, instead of sending, I mean, photonic can allow much larger bandwidth of transmission than electronics. So we decided to, instead of sending in a bit of information, we have an intra-bit modulation. So every bit of information is modulated with a certain code, a certain encryption code. Now we realize the, sorry, the Boolean, 20 minutes? Yeah, sure, no problem. 20, yes. So we realize the linear, the Boolean, the logic gates I showed you before, and we cascade them. When we cascade them, the Boolean operability is destroyed because the devices are linear. But because we have this code, this intra-bit code, despite of the destruction, partial destruction of the Boolean operability, Boolean function, we can still at the output decode the proper Boolean function due to this encryption. And we use now this encryption to realize larger photonic processing circuits that realize 2 by 2 and 3 by 3 matrix multiplication operations, which are the basic building block in every AI processor, artificial intelligence processor. My last thing I wanted to speak about in the last minute of my talk is how to do physical encryption, photonic encryption. So we have developed a concept, a circuit, in which we manage to put our information in the time domain as well as in the spectrum domain, much below the noise level, such that anyone that wants to tap to the information cannot really see that the information is being transmitted. This is done by properly sampling the information in time, which spreads its spectrum, and by adding an encrypted phase in time and in spectrum, which allow us to encode the information. And only if you have the right decoding key, you can alleviate the information above the noise and detect it. Otherwise, you cannot detect it. You can see the gain of tens of dB in which we can lower the information due to our encryption below the noise level. You can see here in this experiment that we have performed that if you do not know the decoding keys, then in this constellation where four signals were transmitted, and you don't know the key, you don't detect them, you detect something else. And if you know the key, you detect the 4 signals. So we can also encrypt information to do a physical physical layer cyber in photonics, which can also be used to transmit information at lower SNR and save power. So to summarize my presentation, I told you that silicon has low nonlinearity effect, and thus it is problematic for realization of Boolean operations and dynamic processing. And I have presented various unique or different solutions involving integration of movable nanoparticles, integration of quantum dots, modified designs that are based on the plasma dispersion nonlinearity of silicon, but do it differently, that allow cascading of linear modules by using intra-bit modulation. I also showed you how photonic solutions can work faster and transmit more information by applying photoactivated logic gates and all optical logic gates. And in the end of my talk, I spoke with you about physical layer cyber technology for stealthy and energetically efficient data transmission. So thank you very much for your time and your attention, and I'm ready to answer any questions
Thank you,
that you
Zev.
have. I try
we
to
have-
speak faster, but if I would have spoken faster, I would not understand what I say.
We have 1 minute for questions. So if you have questions, please.
I have a short comment. First of all, Zev, thank you very much for this really beautiful, fascinating work. I just want to tell you, maybe it can help in some way, that I just came back from a conference in Berlin, and they were speaking about changing the crystalline structure of silicon, people from Eindhoven, where they managed to get completely new optical properties from the silicon by growing a new type of silicon. If you want, I will give you later.
Oh, definitely. Yeah,
Even
I'm
later-
aware of this. This is
Yes.
the alternative. What I wanted to propose is how to use silicon as is without alternating it,
Sure,
almost
sure.
without alternating it
Sure.
in the material level, and yet to realize the dynamic processing that I spoke about.
Sure, thank you, thank you.
So with that, we move on to the next. Thank you very much, Zev,
Thank
for
you.
an
Thank you
excellent
for your
talk.
time.
Very interesting. So while silicon is suffering from quantum mechanical effects, there are attempts today to reduce various quantum effects that originally required heavy equipment to the chip level. And so it is my pleasure to introduce our third speaker today, Ron Follman from Ben-Gurion University, physics, who will be talking about the atom chip. Ron, I'll just transfer the co-host to you. I just have to find you in the list. For some reason. Oh. All right.
Okay, so let me just share the screen. Here it is. So I hope you can now see my cover. Ilan?
Yes.
Yes, you see it. Okay, good.
Okay.
Thank you very much for the invitation. It's very nice to be here and see you all. In the very short time that I have, I want to tell you a little bit about the atom chip, which connects to several of the topics of this session. First of all, it connects to an interesting vacuum. Then it connects to interesting spintronics. And it also has to do with something that connects to electronics. So what you see here is just the atom chip. And I'll give a very brief review. Of course, we use neutral atoms on the chip, and we use laser light to cool, manipulate, and measure the atoms. And this is a typical inframeter signal. So what you see here is actually a concentration of atoms. Maybe I will turn on my laser pointer so you see better. Hopefully you can see now a little red dot. And speaking of spin, we're even thinking of working with nanodiamonds instead of atoms with spin embedded, for example, an NV center in the middle of them. So I'm a little odd addition to this session because I'm talking about atoms and not electrons. But of course, atoms also have electrons and have spins. And there are numerous applications, quantum technology with something we call Atomtronics, and of course, all kinds of fundamental studies. Okay, why can't I change my slides? I don't know. Oh, here it is. So the outline, very briefly, is one slide of quantum technology in our lab. I won't really go into details. Then a quick reminder what atom chips is and what we mean by Atomtronics. That is, the analog for us of electronics. A quick example of our Spintronics. And then just one slide about decoherence, which is really our main enemy when we come to do quantum technology. So quantum technology in our lab, 50% of our work is on quantum technology and 50% is fundamental studies. So just a few examples. We are working with the industry on a compact called atomic clock, next generation of clocks. What you see here actually is this compact clock. And you see here, this red dot in the middle is actually a cloud of cold atoms. And this is mu metal shielding. There's vacuum here, very small vacuum chamber inside. There is a cavity for microwave. There are all kinds of things here. I won't have time to go into it. But this pyramid of mirrors that is needed in order to cool the atoms is actually shown here in a real picture. And what you see here is one cloud is real and all the others are just reflections. One beam coming in for everything, for cooling, for imaging, and so on. This is work done together with Accubit in Jerusalem. All kinds of magnetic sensors. This is work done together with ELTA. What you have here is an all optical magnetic sensor. It's hard to see here, but there is a vacuum cell here made of glass with atoms inside, fiber coming in, fiber going out for spectroscopy. and this is handheld. This is a very small device. Another thing that might interest you is this poster here. There is now a complete change of the SI units system. The most accurate one is the second. And so people are trying to get the optical frequency standards to determine the second in the world. And at Ben Gurion, we're developing an terbium optical frequency standard atomic clock. And we're part of this European collaboration that is intending to make these optical frequency standards the base for the second. Right now, it's microwave standards that is the base for the second, and all kinds of rotation and acceleration sensors. I will not go into that. The atom chip, let me just go perhaps to presentation mode. The atom chip is this is an artist view, just some wafer, silicon wafer, for example, with all kinds of electrodes on it. It's in vacuum, and just a few microns above the surface, there are the atoms. It could be one atom, it could be a Bose-Einstein condensation, it could be a cloud of atoms. And with these atoms, you do the applications, you can move them from place to place. The specific thing you see here is a conveyor belt that can move the atoms in a magnetic trap from side to side, a few microns above the surface, giving us the ability to go around the chip. This is an invention by Ted Hench, by the way, Nobel Prize winner from 2005. And the fact that there are a few microns above the surface, note that they're at nanokelvin temperatures and the surface is room temperature. We don't use any cryogenics. It's very nice for technology. The fact that we don't use any cryogenics, and the fact that there are a few microns away in vacuum means that the coherence times are very, very long. Spin coherence times and other coherence times are very, very long. This is how it looks like in our lab. You see all kinds of electrodes. You see one cloud is real and the other cloud is reflection from the surface. The idea is to try and repeat the revolutions of miniaturization and integration that happened 50 years ago in electronics, and maybe 20, 30 years ago in optics, and now to take a full room like this. This is an optical frequency standard atomic clock that takes a full room now with a vacuum chamber here inside and put it on a chip. That's the vision. And the definition of atom chips is all the time expanding. So if initially we put ground state atoms, now people are putting Rydberg atoms, for example, for quantum computing, cold molecules, cold ions, cold electrons, and now even a collaboration is trying to put antimatter, anti-hydrogen on the atom chip. So this would be the closest approach ever of an antimatter trapped close to a material. The chip itself is really fascinating, the engineering that goes into the chip itself. Right now, the vacuum chambers are large around the chip, but what the plan is that if you hold the chip in your hand, you'll not know if it's a semiconductor chip or a cold atom chip, because the vacuum will be inside the chip. So this is a silicon wafer, just 500 microns or 300 microns thickness. The vacuum chamber is inside what you see here. You have everything inside. You have the particle source here. You have the pumps, vacuum pumps. You have the MEMS to stop, to differentiate between bad vacuum and good vacuum, integrated lasers on it, current carrying wires, electrical electrodes, and so on. Cavity QED and for measuring, and outside goes the information through fibers and electronics. And this is a real life design. Several groups around the world are already realizing this kind of vacuum chamber inside the chip. That's really beautiful stuff. In Ben Gurion, we are fabricating chips for many groups around the world. Here's an atom chip that went to Germany, two atoms or two ions you see trapped here. This went to Amsterdam. You see here a lattice of atoms for quantum computing trapped on this chip. And this is a permanent magnet chip that we sent to the UK for a rotation Sagnac rotation sensor. All right, so if you're interested, there are review papers such as this one that we put on the archive several years ago with many, many references. So the field actually is starting to be called Atomtronics, because we are able to do arbitrary circuits, including transistors and all kinds of other things with barriers, like Josephson junctions, on the surface for neutral atoms. So that's why in analog to electronics, people are starting to use the name Atomtronics. And I think since today we are having a round table discussion about the future of electronics, it would be nice to also know that there is a complementing, angle. It's complementing. It doesn't come to replace. Maybe some of the things it could do better. This complementing angle is called Atomtronics. By the way, I apologize that I would not be able to be in the roundtable discussion today. I simply have another meeting. Sorry for that. All kinds of circuits. For example, these circuits that you see here. For
2 minutes.
2 minutes. Okay, there's a lot of issues about fabrication. We have to go down to nanometer resolutions. I don't have time to talk to you about that. I can just tell you the atom chips have already made it into space. This is the German Space Agency with an atom chip rocket. This is now in the International Space Station. Companies that do quantum computing or do other things with atoms or ions are now already working with this kind of chips. This is a chip that we're doing for the US Air Force. Interferometry, this is part of what we're doing. This is Spintronics, because we're doing Stern-Gerlach type of interferometry, and Stern-Gerlach, as you know, works on the spin of the atom. So we're doing a lot of Spintronics in the sense that we are entangling between external degrees of freedom like momentum and position and the spin of the atom. So it's spin-dependent forces and many kinds of applications. And I have to, somebody's talking together with me, sorry. And decoherence I will not have time to talk about, but these chips, the main issue, of course, is decoherence. And a lot of material engineering is going into suppressing decoherence. And let me conclude by saying that we're coherently integrating different systems and phenomena on a chip. It's ranging from 0.1 nanometer, which is actually the atom itself, all the way to 1 micron scales. All of this has to be coherently integrated to allow for quantum operations and functional atomtronics. The atom chip is still far from realizing its full potential, so many groups around the world are working on it. It's expected to have a lot of impact on quantum technology. I already showed you 2 companies, and there are more companies that are working with chips and neutral atoms of different kinds or ions. And atomtronics may have a nice complementing angle to electronics. And I thank you very much for your attention.
Thank you very much for your talk. Excellent talk. It was very, very interesting. We have now 2 minutes for questions. So if anyone wants to ask a question, this is the time. Let me ask you. I mean, you only mentioned briefly qubits. Can you spare some more? Say
sure,
some more.
So any two-level system of the atom is a qubit. So people do with these qubits everything. So for example, we do atomic clocks, and that is a qubit. We have to use a qubit to measure time. Two-level system. We do magnetic sensors. That's a qubit. So any two-level system is a qubit, and you also need a qubit for quantum communication. You need a qubit, of course, for quantum computation. So these neutral atoms, simply you choose a two-level system inside the atom that is convenient to work with, and that's your qubit. And this qubit survives a few microns above the surface, the room temperature surface of the atom chip, and so the qubit has a very long lifetime.
I think the main question is how you entangled few qubits in those chips. This is the hard one.
Yes, so of course, depending on what your application is, but if people want to do, for example, quantum computing, so the figure of merit is the ratio between coherence time of the qubit and the operation time. You want to get at least 10 to the 4 operations within the coherence time. And it's true that, for example, very short coherence times of superconducting qubits can still have very effective protocols because their entangling time is very, very short. On the other hand, today, neutral atoms with Rydberg states are pushing down all the time the entangling time between atoms. So I would say that the jury is still out, or for example, the company IonQ, which works with atoms and is tangling them through the motion with the charge. And so all of that means that the jury is still out on what system will eventually give the best results. But I would say that neutral atoms and charged atoms, ions, are still in the game. If we're talking about quantum computing, other applications, they're definitely in the game.
Okay, thank you very much. And it was excellent talk. We enjoyed it. And now, today, there's a great interest in materials that have the natural capability to filter spin. It is a pleasure to introduce Leo Kronik of Weizmann Molecular Chemistry and Material Science. Leo will talk about a theoretical study of such filtering in a very special material. Leo, the stage is yours.
Thank you very much, Ilan, for the kind introduction. I hope you can see my screen, which I just shared. Yes?
Yes, I see your screen. Perfect.
Oh, very good. Okay, so today I will tell you a little bit about our work, which is theoretical, on understanding collective effects that drive molecular spintronic devices. Hang on, I see that I have some problem with the sharing here. So I'm going to have to do that again. Apologies. Let's start over. Okay, I think it's working now. Okay, so first of all, what is molecular spintronics? So as demonstrated in this very nice overview in Nature Materials from a few years ago by Cornia and Seneor, molecular spintronics can be viewed as a field which is somewhere between molecular electronics on the one hand, organic spintronics, that is spintronics that involve organic materials on the other hand, and also we can think about it as a subset of molecular magnetic phenomena in general. And so it's somehow at the intersection of all of these different topics, and therefore somehow also at a very interesting intersection between physics and chemistry and material science, which I think is very appropriate for this conference in general. So ultimately what the molecular spintronic device boils down to is something that looks like this. I have some leads, they are typically metallic. I have some molecule which is anchored to both leads. That's the canonical setup of molecular electronics in general. But now in molecular spintronics, I am interested in some spin-related property of the electrons that try to traverse this junction. So I expect that somehow, at least in some property, the fate of the electron going up with spin up is going to be different from the fate of the electron with spin down. And so I will have some interesting spintronic effect. So that's sort of the general playing field for today's talk. And before I proceed, I would say that an important theme of the talk is that a molecular electronic device is really a special case of an organic-inorganic interface. And an organic-inorganic interface is generally of much interest because generally speaking, I cannot describe what I see fully with either a molecular or a solid state picture. And I will usually have an unusual set of collective effects from the interaction between the organic part and the inorganic part. And to understand what I mean by that, we can look at the classical analog, which is a pebble beach that you see in the picture here. So you can think about the wave part as corresponding to the delocalized electronic structure, like the Bloch waves in a metal. You can think about the pebbles as the localized electronic structure with each pebble corresponding to a molecule. And then even so, you see that there are interface phenomena where the waves hit the pebbles. So of course, this is completely classical, but this carries over sometimes even more dramatically to the quantum world. And in this lecture, I will illustrate all of that through a set of joint work that we have done with an outstanding experimentalist, Orenthal at the Weizmann Institute, whom you see on the left here. Originally, I was hoping that I would have enough time to also talk about a different collaboration with other outstanding experimentalists, Raman at Weizmann and Yossi Paltiel at the Hebrew University, but I'm afraid I will not have time for that today, so I will focus on the work with Oren. So what you see here is a set of so-called atomically wired junctions involving benzene. And what that means is that unlike most cases in molecular electronics, there is no binding group. It's really direct binding between the metal, in this case platinum, and the molecule, which in this case is benzene. And this direct binding has all kinds of interesting consequences for transport that are described in this paper. I will not go into it, both because it's slightly older work and because it's not spintronic yet. But the point that I would like you to take away from this particular work is the figure on the left, where you see some of the computed orbitals for this system. So you see that the orbitals are all over the entire system, which means that if I ask you, well, does this particular orbital belong to the molecule or to the metal, then actually the only reasonable answer is that it's a poorly phrased question. The orbital clearly belongs to both, and that is because there is significant hybridization between the pi orbitals of the benzene ring, and in this case, the d orbitals of the platinum, which also comes out of the calculation. So as I said, this is not a spintronic application yet, but now if we accept this principle, this actually opens the door to an interesting idea that does involve spintronics, and that's the next step. So we know that generally speaking, spin polarization in transport through a metal ferromagnet is a fairly limited phenomenon. Why? Because if I think about a traditional ferromagnet, say iron or nickel, then I know that the magnetization itself is dominated by d orbitals. They are spin polarized, but they barely contribute to the conductance because they're not at the Fermi level, they're far below it. So the orbitals that are at the Fermi level are typically s orbitals, but they are not so polarized. So it turns out that you can have a magnet, even a very strong magnet for that matter, which would still be a fairly weak material as far as spintronic applications are concerned. An extreme case of this general idea is something that we have done quite a number of years ago with Chris Palmstrom and Paul Crowell. You can see the reference down at the bottom of the page, where we looked at the traditional spintronic interface between iron and gallium arsenide. And we could see that because the electrons that control magnetism are not necessarily the electrons that control transport, you could even invert the spintronic effect. So you could have a magnet pointing up, and yet the electrons that are transmitted preferentially are the ones pointing down. So the bottom line is that you're not really making the most of the magnetization that is afforded to you by the natural properties of the metal. Well, so if we accept the idea that in this junction involving benzene, there's actually a lot of hybridization between the d orbitals and the molecular orbitals, then maybe through their hybridization, you can actually get to the point where you can overcome this. You can promote the transport via d orbitals and somehow block or at least reduce the transport via s orbitals. So Oren's group tried that. And now it's the same molecule in the middle, benzene, as before, except that now the metallic lead is nickel, which is obviously magnetic. And the question is whether there is an amplification of magnetotransport effects via this pi-d hybridization. Now, Oren's group measured that through anisotropic magnetoresistance, namely the idea that the conductance of a ferromagnetic metal would depend on the angle between the current and the magnetization. This is a known effect, albeit a small one, even for bulk nickel. It's just 1.5% or so, but it's an indicator of spin polarization. Two different groups have shown already 15 years ago or so that if you take this down to an atomic junction, it's a larger effect. It's about 10%. But with this benzene molecule in the middle, Oren's group was actually able to measure an effect of more than 200%. So that is a huge effect, which obviously got our attention. And we wanted to see if we can contribute to its theoretical explanation. Now, a direct computation of anisotropic magnetoresistance is not so simple because it involves various assumptions about the spin-orbit coupling and, more importantly, various scattering mechanisms. So we didn't go there, but we didn't need to because we could get the answers that we were looking for just by looking at the spin-polarized density of states. So my postdoc, Soumyajit Sarkar, calculated the density of states for this junction. What you see on the top figure is the partial density of states for spin up on the top and spin down as a mirror image on the bottom. And you can see that close to the Fermi level, which is what would dominate spintronics, you really have a large spin polarization. So the average spin down of pi electrons is not the same as the average spin up. And in fact, if you take a small window around the Fermi level and plot the actual orbitals there, you'll see that the spin down orbital really builds a bridge from one nickel to the other through the benzene molecule. So you can expect reasonable conductance. Whereas in the other spin channel, you don't even see a continuous distribution. So it's not surprising that you would have spin polarized transport. And it is clear that it is entirely brought about by this selective hybridization process. So this is one example where we can use a collective effect in molecular electronics in general to promote a spintronic. The second example I would like to show you now, and then we take it a significant notch further, is, well, can we use such ideas to create a single molecule spin filter even without magnetic leads? So now we go back to non-magnetic leads, which is silver in this case. So of course, some spin distinction has to come from somewhere. So in this case, the molecule is spin polarized. It's a vanadicine molecule, which you see on the left here. It's a one vanadium atom sandwiched between two 5-fold carbon rings.
Your 2 minutes.
Sure. So this has a net spin, but it is not a molecular magnet because there's only one magnetic atom. There is nothing to interact magnetically or antiferromagnetically, etc. So how would you go about measuring spin polarization if the lead is not magnetic? You can't do magnetic resistance. So what Oren did instead, which is I think quite clever, is to rely on shot noise analysis. In a shot noise analysis, one can show that there is a noise coming from the individual motion of electrons. It is related to a term known as the Fano factor F. The Fano factor is related to the partial transmission or reflection through each transmission channel, which also depends on spin in this form. And then, of course, the conductance is the general summation over all of the transmission channels. And one can show that the probability for a spin polarization is related to these two factors. It has to be greater or equal than some combination of the Fano factor and the overall conductance. So one can use that to create a plot that looks like this, where we take all kinds of possible transmissions. For each, we calculate the Fano factor and the conductance, and we make a plot. So the dark gray areas in the plot means that it never happens. There is not a single point of data that falls in there, even theoretically. The gray areas mean that it's possible, but it will be spin polarized to varying degrees. And the white area means that it's possible and there is no spin polarization. So then we superimpose this with the actual experimental data, which are the various red dots. And we see that, first of all, none of them fall in the forbidden area, which means that the theory is reasonable. And that many of them do fall in the region where you have spin polarization, even as much as complete spin polarization, 100%. And as a control experiment, we did the same with ferrocene, which is very similar, except it doesn't have a net spin. And then indeed, experimental accuracy, not a single data point is within the spin polarized. So the remaining issue theoretically, and this would be my final slide, say for the conclusions, is to show where this comes from. So first of all, it's not clear a priori whether the molecule is absorbed in or is captured in the junction in a parallel or a perpendicular configuration. So we computed both, and then we computed the transmission for both. And we saw that there is a significant spin polarization in the transmission for the perpendicular configuration, but not for the parallel one. So we believe that when we see spin polarization in experiment, it's because of the perpendicular scenario. The perpendicular scenario does indeed come again with a significant spin polarization in the density of states. But there is one final significant riddle here, and that is that if you look at the polarization in the transmission, which is this block D here around the Fermi level, it can be as much as 100% ideal polarization, even though the polarization in the density of states is not that high. It's only around 60% or so. So the final riddle for us was, how is it at all possible that the polarization in the transmission is actually higher than that suggested by the density of states? Usually it's the other way around due to some scattering. So here it's not only not lower, it's higher. Turns out that this is an interesting quantum interference effect. You cannot tell that directly from the first principles calculation, but you can fit the first principles calculation into a tight binding model, which was done by Alex Mogunov at the University of Paris. And then one can switch on and off different transmission channels, and one can see that actually there is transmission through the rings, through the vanadium atom, and through all paths, and they interfere constructively so that the overall transmission is actually larger than the overall net polarization, which is yet again a very interesting quantum collective effect. So that brings me to my conclusions. I hope that in this short talk, I was able to show you that collective effects are a driving force for novel effects in molecular assemblies in general, and specifically in molecular spintronics, which can obviously be of technological relevance. And the last example, for example, is a spin filter. And I hope that I was also able to show you that first principles calculations allow us to confirm, understand, and ultimately even predict such phenomena. And this helps with new intuition. With this, I will stop. Thank you very much. I'll be happy to take questions.
Thank you very much. It was a very interesting talk. We have like half a minute for questions.
May I ask a question, Leo? Does it matter if the molecule is chiral or non-chiral?
It does, not in the context of this specific experiment, but in the context of the experiments in Ron and Yossi that I didn't have time to show. Absolutely, there is a strong effect known as chirality-induced spin selectivity, the theory of which is now partly, but definitely not completely understood. And actually, a bunch of us got together for a workshop on that, and the outcome of the workshop, which summarizes the state of the art in the theory, will come out in Advanced Materials soon. So yeah, that's a whole topic in itself, not relevant for the work with Oren that I showed today, because obviously benzene and vanadicine are not chiral, but generally of very much interest, and I didn't have time to talk about it today.
Thank you.
Thank you very much, Leo. Now our next speaker is Yaakov Tischler of Bar Ilan. He will talk about applications of Raman spectroscopy in characterization of nanoscale layered materials. Yaakov, the stage is yours.
Okay, how do I share the screen? Do you want to continue? Yes, hold on a second. There we go. 1 second.
I see your screen.
Let's try this. Okay, thank you, Ilan and organizers, for giving me this opportunity to share our work on using low frequency Raman to characterize nanoscale, nanostructured layered materials. This work was really done by Bharti Rajaswan from my lab in collaboration with Rajashree Konar from Professor Daniel Nassim's lab, along with Chagit Aviv and Professor Ilya Greenberg. And we've been funded by the MOST, the Ministry of Science and Technology. So let me give you a little bit of background about Raman spectroscopy in general. C.V. Raman was the first Indian to win a Nobel Prize. Typically, when you shine laser light on a sample, some fraction of light will be reflected, some fraction could be transmitted right through and absorbed, and then there's a tiny fraction that's actually scattered. Okay, and where does that scattering come from? So it's not absorbed, reflected, or transmitted. So basically, when you shine a laser, for example, on the material, the laser itself, due to the polarizability of the molecule, the laser will induce an optical transition dipole within the material, and then that optical transition dipole can radiate. So typically, the wavelength that's radiated is the wavelength that is shined in the material. That's the most logical. That's the most logical frequency in the problem. However, what Raman realized is that a slight fraction of the scattered light is actually shifted to different wavelengths due to the fact that the materials itself have their own internal vibrational resonances. And so if you have a setup where you shine a laser on a material and you block carefully the laser light and also the Rayleigh scattering, which is coming at the same wavelength you put in, you can see these small changes in wavelength due to the Raman scattering. And a typical Raman spectrum may look something like this. So in this case, the excitation wavelength is 532 nanometers, and we'll see peaks that are red shifted, otherwise known as the Stokes Raman scattered, as well as peaks that are blue shifted, the anti-Stokes peaks. And typically in the spectroscopy community, one looks at this in terms of wave numbers because wave numbers scales linearly with energy. And so the area that we're going to focus on today is low frequency Raman scattering. So in low frequency Raman, in this case, in a microscope, micro Raman setup, one might have a laser, couple that into a microscope, then get this light back out. And then the magic sauce is these special filters. In this case, it's a series of 3 filters. These are called volume holographic filters. And what's special about these Raman filters is they have a very, very narrow stop band, about 10 wave numbers. So if you look here at the Raman, at the low frequency Raman scattering, you can see there's only a small region, about plus or minus 10 to 15 wave numbers, that's actually where the laser is blocked. Well, I really like this spectrum. This is one of the first studies we did, led by Chagit Aviva, my lab, in conjunction with Irina Nemstev and Professor Mastai's lab, where we looked at the low frequency Raman of a chiral crystal, nanocrystallite film of aspartic acid that was all in the L form, as well as a racemic mixture that was both D and L equally mixed. And what was very surprising is that even though the regular Raman of both L and DL crystals have basically the same spectrum, because they have the same chemical bonds and the same chemical fingerprint spectrum, when we looked in the low frequency Raman, we saw very, very big differences. For example, the L has this peak around 50 wave numbers, which is completely absent from the racemic mixture. And the way we understand that intuitively, we did some analysis as well, is that if you look at a chiral crystal, if it's entirely L or if it's entirely D, it's going to have one kind of packing on the nanoscale. But if you have the racemic mixture, those slight twists and turns in the chirality is going to make a small change on the nanostructure, and that small changes in the nanostructure become apparent in the low frequency regime. So I would argue, and this is the direction we've been following for some time now, that the low frequency Raman scattering range is really, really well tuned for studying very small differences in nanostructure. Now, if I told you, if I would create the impression that this is new, that would be misleading. I had a professor, Arto Namiko from Brown University, who always used to say there's a 30-year cycle in research. So if you want to know what's happening today, look 30 years ago. If you want to know what's going to happen 10 years from now, look 20 years back, right? There was a whole bit, there still is a huge effort in plasmonics. Look back to the 70s, we had that there first, but you didn't have the E-beam technology to make a lot of those amazing structures realizable. Well, if you go back 30 years ago, and it's still today, you can do low frequency Raman with these triple monochromators. They're very big, very heavy, and they're amazing. But what's made this new revolution now is the fact that you have these things called volume holographic filters, which for very low cost, relatively low cost of a few $1,000s, you can get these 10 wave number stop bands for your Raman filters. Now, let me give you some examples to build up the intuition of where low frequency Raman is applicable for characterizing nanostructure. Here's an example from a few years ago, 20 years ago actually, where this group was looking at quantum dots. And looking at the low frequency Raman, you could see that there's changes in the low frequency Raman depending on the size of the dot. As the dot becomes smaller, the Raman scattering gets larger. So this is very exciting for metrology, right? Because Raman, and especially low frequency Raman, becomes more sensitive as your structures get smaller. And intuitively, this was explained to me by Professor Igor Lubomirsky from the Weizmann Institute, where he said, think of it like this. If you have a certain speed of sound for this material, and then you have a certain radius for your nanoparticle, so the frequency is basically going to be set by the speed of sound divided by the radius. So you have basically this linear relationship between the Raman scattered frequency, the low frequency Raman scattered, and 1 over the radius, as this group showed. LFR is also very sensitive, not only for size characterization, but on the nanoscale, but also for characterizing layered structure. These are some very beautiful MBE grown superlattices made out of semiconductors. And you can see that when you look at the low frequency Raman, not only do you see the bonds of, if you have a silicon germanium superlattice, not only do you see the bonds of silicon germanium or silicon, but you actually see a whole manifold of states called the folded acoustic phonon modes, which are actually correlated to the thicknesses of the nanostructure. So we can learn a lot about the nanostructure from the low frequency Raman regime. Now, how it ties into layered materials is actually, they're also
1 minute.
1 minute, wow. LFR is very, very powerful by looking at the shear modes or breathing modes. And we've used this now to characterize TMDC type materials. So for example, you need to have a Raman quiet substrate. In this case, we looked at molybdenum diselenide, and you could see based on the number of layers differences in the Raman spectrum in the low frequency regime. And let me just say one last thing is always in Raman, because it's a photon star process, we're looking for enhancement methods. We found that we can actually enhance low frequency Raman using dielectric structures. So here's an example of tungsten disulfide and different structures actually show significantly enhanced Raman scattering. And with that, I want to thank you for listening, open it up for questions, and thank especially Bharti, Rajashree, and Chagit for their work on this, and our sources of funding, the Misrad Madav and Technologia and the Israel Sound Foundation. If you have any questions.
Thank you very much, Yaakov. And while I shift to the next, the co-host to privileges to the next speaker, we have maybe half a minute for questions. Okay, so thank you very much for a very interesting talk. And now we shift to Sabrajit Mukherjee from the Technion, who will tell us about a very interesting heterostructure. Sabrajit?
Yes, I'm sharing my screen. Can you hear me? Can you hear me?
Yes, I can hear you, but okay, I see your screen.
Okay. Just something is going wrong. Okay. Thank you very much for giving me the opportunity to present my work here. I am Sabrajit Mukherjee from the Technions, from the Faculty of Science, Material Science and Engineering Department. Today, I'm going to talk about the optoelectronic modulations of the two-dimensional materials, which is integrated in a monolithic circuit, which works for the multifunctional devices. So this talk is very much related to the talk given by today by Andreas Case. He already talked about much about the size shrinking and the problems of the electronic devices. Basically, today's electronic devices facing the challenges for the low dimensional approach. We already reached the scaling limit by using the current technology, and we need a higher density interconnectors between the different components of the electronic circuits to shrinking down the volume and continuing the technological progress, so that the possible solutions for this technological progress would be the photonic integrated circuit. The photonic integrated circuit is basically the circuit which is controlled by the electronic, also the optical operations. It has many components like source, detectors, many modulators, and main idea is to replacing the electrical interconnect. Replacing the electrical interconnectors by the optical communications. So there are many advantages. First of all, optical communications has a higher bandwidth, and the speed of the light is much faster than the electrons. So the communication speed will be very high. And if we don't have the electrical interconnects, then we can eliminate the Joule heating problem, which is the main source of heating of the devices. So in these directions, people are tried many materials like group 4 silicons, photonic, or group 5, 3-5 materials like gallium arsenide or indium phosphide. And nowadays, people are looking for the advanced material, which is basically the 2D materials. There are many 2D materials are available, and it is very much useful or beneficial to using this 2D material, because we can scaling down the gate length also due to its thinness of this materials. Also, if you see this, we are mainly working, there are many 2D materials are available, and we are mainly working on the indium selenide. So why are working on the indium selenide? Because indium selenide is some unique structure. First, it offers the, it has many phases. So it offers the phase dependent band gap. So according to your application, you can choose what type of material you need. And most interestingly, the alpha phase indium selenide is a ferroelectric. And so it also offers the intercoupled ferroelectricity. That means it has the in-plane polarizations, also the out-of-plane polarizations, and you can control one of them by controlling the other. Next, we jump to the to show some results of this ferroelectric behavior of this indium selenide. So we using the Kelvin probe microscopy to find out this ferroelectricity instead of the piezoelectric microscopy. Here we make a field effect transistors, and we grounded the source and drain, and then measured the potential between two electrodes. And by applying the gate voltage, we see there is a slope changing from positive to negative side. So from this, we can calculate the electric field associated in this channel, which is basically the derivatives of the surface potential with the length. And we found that the gate voltage can change the electric field between this electrode, which is associated with the in-plane ferroelectricity. So basically, we are rotating the out-of-plane dipoles by applying the gate voltage. Then we withdraw the gate voltage and map the devices. We have a very nice hysteresis loop here, what we got from the Kelvin probe measurement, and it also have a high retention over the time scale. Then we check these devices for the photoresponse behavior. So we first at the fresh state we measure the responsivity, which is about 30 ampere per watt. Then we pull the device with a positive gate, say per 100 gate. Then we draw the gate, and we again check the photoresponsivity and do the similar things for negative pulling. So we see for both cases, the pulling changed the photoresponsivity a quite lot. But the range of this change is not very high. It is only from the 20 to 40 ampere per watt range. So we decided to go for the heterojunctions devices because the heterojunctions might have increased the enhancement factor. And we choose the post-fabrication process to change the device property to make the heterojunctions. So we decided to go with the laser illumination, visible laser illuminations, and check if the laser illuminations can change the electrical as well as the optical property or not. So this is the TEM microscopic images. This dark area is actually the laser illuminated area, and the bright area is the pristine indium selenide. And we found this nice nanocrystals are formed under the laser irradiation area, which is basically the indium oxides. We also check the PL and Raman of this laser irradiated area, and we see the PL and Raman intensities also changes. We also do the top sense characteristics to see how far we can change the property of this. The green lines are actually the indium oxide and red are indium selenide. So it is possible to change the whole film thickness by using the laser irradiations by choosing the optimized conditions. These are the also this can change the surface potential, which is related to the electric property of the devices. So this is the optical images corresponding surface potential and Raman map. So the next question is this, that this irradiation can change the device property or not. For this, we fabricate a FET again and do the surface potential mapping as previous. And we see that the pristine indium selenide has this type of surface potential, but when the channel is converted to the converted to the indium oxide is changes the electrical conductivity, and we then we characterize the memory effect of this indium selenide part and indium oxide part, and we see there is a hysteresis loop for the indium selenide part, whereas there is no hysteresis for the indium selenide part. We also tested the photoresponsivity of these heterojunctions, and we have a almost 15 type photoresponsivity enhancement. Also, we have a wide band photoresponse over the 450 nanometer to 750 nanometer range. Then we also tested the optoelectronic memory effect, where we use one input as an electrical input, another input is an optical input, and we have a multi-level photoresponse in these devices, which can be used as a logic gate of the device, which can be used as a logic circuits or some logic operations. So in conclusion, we fabricate a post-fabrication. We fabricate the device by using a post-fabrication technique where we can fabricate the indium selenide and indium oxide heterojunction devices. The indium oxide has a high conductivity, and the heterojunctions offer like a 15 times higher responsivity than individual components, and it can be used as a logic operations by using light as a one input, another input is a electronic input, and at the output we can get the modulations. So we are very much thankful to the organizing committee to giving me the opportunity to present my work. I also thankful to Professor Ilad Koren to giving me the space in his lab to work in this area. And we are also thankful to the Ariel Smith from TIAO for providing us the CVD sample for working on it, and RBNI for the excellent nanofabrication facility. Thank you very much.
Thank you very much for a very interesting talk. And we are right on time to move on to the next part of this session, which is going to be a discussion. I'll just please bear with me. I'll just transfer the co-host privileges to Yossi. So we will now turn to our roundtable discussion, and discussion will be moderated by Yossi Paltiel from the Hebrew University, and Uriel Levy, is he here?
No, he couldn't come in the last moment. So
okay.
The
subject of the discussion is the future of electronics. Yossi, the stage is yours.
Okay, so I didn't put a virgraph, but I think we should start from what the first lecture was talking about, that we are now about 2 orders of magnitude above the thermodynamic limit, which means if we can go at least improve by 100 times better using standard electronics, or getting closer to the thermodynamic limit in the memory devices. And of course, where we can go also to quantum devices and use even more interference. So we have seen here several technologies, and I think the main issue is to discuss what we think will be the best technology which will lead us to this thermodynamic limit classically, and of course, what will be the best technology which will lead us to quantum mechanics, or to the best quantum mechanics. So I think, Zeev, you had an idea saying that it's a photonics. Maybe you can convince us.
Yeah, I think that the next emerging technology will involve developing of photonic standalone AI processing circuitry that will be able to communicate with other processors. The main leap that will allow this is the fact that photonic could not before be a significant player in processing in the world of processors, was because it was always an aid to solve bottleneck of what the electronic processors could do. So photonics was never a sufficiently generic processing unit. But since the development of neural networks and deep learning and AI and so on, and AI structures could be realized with photonic models in a relatively simple way, I believe that the next step will be a developing of generic photonic processor that will be a standalone processor that could assist in big tasks like data centers, but also in small tasks like sit in autonomous cars that need to perform a lot of AI-related processing, training, and inference. So this is my belief, and the main motivation for this field to evolve is related a lot to the latest evolution of the field of optics communication that allowed to develop fast modulators and integrated circuits that could inject the information to the photonic standalone processor in such a way that the interface to the external world is now feasible. Something that was not feasible, say, 10, 20 years ago, because there were no fast modulators that consume low power and so on. But now there are in the world of optics communication, and the development of processing methodologies based on neural networks could divert the technological capabilities towards developing of an agnostic standalone photonic processor.
Okay. Although I think the neural networks, you don't control exactly the logic. So if you think about logic, you just control the results because people don't really know how to follow the result. But this is interesting.
No, you can train the network. So you apply a training sequence, which can learn certain different types of problems and then do inference on problems that are within the same category. Could be classification, recognition, could be different type of tasks for which the network could be applied for.
Okay. Leo, do you have something to say about Spintronics? Spintronics has always been considered the best way to go, one of the ways to go to downscaling. But if you think about it, so far we just talked that we have less scattering, so in principle we can work in higher frequencies, but other than memory devices, the giant magnetic memory, there's not many Spintronics devices working in industry so far.
Yeah, that's exactly right. So Spintronics is a success story technologically in the sense of the memory that you just mentioned. That's absolutely correct. Less of a success story as far as electronics is concerned, at least so far. In other words, the issue of semiconductor Spintronics, although it exists and has been demonstrated in the lab at least 20 years ago, depending on how exactly you count, maybe a little more, it has not matured to a technological product. And I think that's a question of several factors, including the temperature at which you can operate it, and how controllably and reliably you can really manufacture large-scale devices. So I think the promise is still there, for example, in terms of better signal-to-noise ratio, in terms of combining processing elements and memory elements on the same chip. So for example, the memory transistor based on Spintronics, again, has been suggested something of the order of 20 years ago, but as we know, is not a commercial reality because of the obstacles that I just mentioned. So I think that the possibility is there. It's still very interesting, but there are major, I would say, technological and commercial hurdles to getting this done. I would say more generally that, silicon technology as we know it has been around actually exactly for 50 years. A few days ago was the 50th anniversary for the first microprocessor that Intel released, 4004. And it's so well entrenched and so successful that you would really need something that offers massive advantages, not only to replace it, even to create niche applications that do not depend on it. You really need to come in with a major disruptive advantage to make this happen. So a lot of technologies, came and went because they ultimately couldn't compete with the success of silicon.
So you believe that somebody will replace something will replace silicon, or
not tomorrow morning, that's for sure. But I think in the long run, eventually we will hit some barrier with silicon as we get, if not the thermodynamic limit itself, then approaching it will become increasingly more difficult. And then ultimately there can be something coming out of nowhere right now that will replace it. Out of the technologies that we now consider, I think that many of them, including the optical technologies that Zev just mentioned, have a lot of potential to supplement various issues and to outperform in specific applications. But I think there is no real candidate at the moment that can blow silicon out of the market, so to speak.
Yeah. And this is the case. The thing is, I think when you go think about those issues, it's the number of investments that have done in the silicon photonics.
Yes.
Yes, it's very hard to remove the train, even if you find something which is a little bit important, like the joke about gallium arsenide. It's a material of the future and it will always stay so.
Exactly.
Exactly.
It was the same thing with tube technology. You know, when transistors came, tube technology was still running for another 20 years after transistors. So it takes time to actually an existing technology to step down, right? So especially silicon, which is like trillions of dollars investments.
Yeah,
but I think the main problem is that our computing technology is based on switches today. This is the way we think. Like everything we consider is a switch, and the problem is coming from this switch. We want to make this switch faster, then have to make it smaller, and there's a limit to how much small you can make it, and so eventually you will need to go to something else, and which is probably I mean, now we are facing all these problems with tunneling, right? And basically the technology of CMOS is not built for quantum mechanical effects. It's just it's being killed by quantum mechanical effects. But the future is probably, I think, in technologies like the quantum computer, which is a totally different thing, where the speed is gained by something else, not by making the switches faster.
No, I think that too, if you talk about different, not talking about switches, this is of course what Zeev was talking, neural networks, which is now a big revolution in computer science, where you have the learning networks, and then you don't need a switch, you just need a result which can be induced or changed by time to time as a machine learn how, if you have enough data, you can learn and understand. So this is a new kind of computing. As the other way is, of course, quantum computing. But the thing is, for quantum computing, I think that we are far from being, I'm not talking about connecting 100 qubits. If you do really want to do real-time computing, I think we are far away from that, because you need just, let's say, fractionalizing of the numbers. You need 10 to the 6 gates and 10 to the 12 control gates. We are very far from this. But if somebody wants to add, I will be happy to hear. Yes. Okay, so what I think is that we have, if I look or when I try to think how to, what did I say? First of all, I think we have the classical question is, where do we go classically from here? And I think optic is one direction, Spintronic, of course. And of course, we heard things about the 2D material, which offer a material system which is very, very, the van der Waals material, which could be, again, a way to reduce size and improve devices. So far, there were many devices out of this, not that we are working much faster with this kind of thing.
Reducing size is actually, yes, it's actually limited. I usually give in class I give the example of the one atom transistor, which is not actually one atom. It's like 225 atoms, but still, I mean, there's a limit to going down. Even if you use 2D materials, how much can you go down? So this direction is naturally limited. We don't have enough.
No, but I think, as was mentioned in the beginning, we can improve in frequency operation, at least by 2 orders of magnitude, which is a lot. And I think a lot of the silicon map goes to frequency and not exactly to size. And of course, it's 3D. We can also build 3D memory devices and have much more dense memory devices. Zeev, do you have something to say?
Yeah, I agree to the discussion. I just wanted to say that whatever I said before is definitely should be combined with the effort of doing it on silicon. So definitely changing silicon to another platform will not happen. So the research should be diverted into two parallel paths. On one hand, how to realize the optimal processing configuration by building the right neural networks and by properly interfacing it with the external world that will inject the information to the optical processor. And in parallel, there should be an effort which is more related not to processing or to optics, but rather, or to electronics, but rather to material science of what is the optimal way for those design devices and structures to be integrated on top of the silicon platform, such that they could work with silicon, they could assist with the conventional electronic processors realized on silicon, and so on. So it's a joint effort. Yeah, sorry.
So my real problem, my real problem is that, let's say that we have the optics and we have the silicon, then usually what takes the most time is to transfer between the optics and the silicon. So unless the optics is doing a lot of things, you don't gain a lot. So we don't have a way to work only on optical computing, and we are using always then again the silicon in the end. So
no, but this is what I said. I don't fully agree with this. This was correct until a few years ago, where the photonic processors were not generic enough. They could do only very specific tasks. But with the advances of neural networks as processors, with AI processing, with training and inference, you could make the photonic processor to be a standalone and a more generic processor that could properly interface with the external world while it does its own processing task, and not only a task that depends on some other tasks done in the electronic processor in parallel, in my opinion.
Yeah, no, I think we are now in exactly in the junction. We need to see if we can do that or not. Thanks. Leo, do you want something to add?
I think only in the sense that, you know, again, it's a multidimensional problem. For example, I think much of the strength of modern electronics, as we know, is not necessarily from the performance of an individual transistor, but rather from the fact that you can pack so many of them into so little space and gain from the combined performance or action. So I think that as we analyze what is suitable and what is not, we should keep everything in mind. The possibility of large-scale integration, the possibility of what is the response time for each device, the possibility of multiple functionalities such as memory or other additional issues. And there may be niche applications where one is more important than the other, but we have to consider the overall picture. For example, on paper, indium antimonide is a better semiconductor than silicon, at least as far as speed is concerned. It was actually even on the Intel roadmap for a while.
Yeah.
But realistically, are you going to integrate indium antimonide transistors to the extent that you're integrating silicon transistors? Then spoiler, the answer is no. So it never went anywhere. So I think it's really important to ask yourself, what's the application and where do I need to be in terms of a various set of parameters in order to see if I'm competitive with existing technologies or not, or potentially competitive after sufficient R&D.
What about theory? If I talk about improving first principle calculation, of course, using the networks that Zeev was mentioning, or quantum theory or quantum computing?
Yeah, I think that will play an increasing role, both in terms of identifying materials, in terms of simulating possible scenarios, but it always goes beyond that. In other words, even if the calculation identifies something as promising, That's the beginning of the process, not the end, because then you have other considerations like integration, like reliability, like cost, which you will not see in the calculation. The calculation can help you trim down the field so that you don't waste your time and effort on efforts that are doomed to fail from the beginning.
Okay, yeah, with this I agree. Ilan, do you want to conclude or?
Yes, it's really time to conclude the session. So I thank all the speakers again for their interesting talks, and I thank all of you for who took part in our session. And I just want to say that following this session, the same Zoom session is going to continue and to be used for a poster flash talks. We let the poster presenters also present the posters with a 1-minute talk, and this is going to take place right after this session. So so those who are the presenters of the flash talk, please stay with us. And with that, I conclude. I thank you very much for a very interesting session. And,
one thing more, that I think this session shows, and as the discussion says as well, that we are now in an interesting time where we are moving forwards and to try many other things, some of which we are talking about. So I think especially for the students, this is a good time to be a student, so enjoy it.
Right. Thank you.
Thank you. Goodbye.
Thank you
Have
all.
a nice day.
Bye.
Bye-bye.
Bye. So now I will share the and does everybody see my my screen?
Yes.
Yes.
Thank you.
Yes.
Okay, and let's see. So the first flash speaker is Ruti. Is she with us? Me?
Hello, am I audible?
Okay.
Hello.
Yeah, this is it. So please, you have 1 minute to present your the poster.
Okay, sir, can I start?
Yes, yes, we can start. Please.
Okay, hi everyone. The topic of poster presentation is synthesis of reduced graphene oxide using adsorbing acid for supercapacitor application. As we know, the synthesis of reduced graphene oxide has been a concern due to use of standard reducing agent like hydrogen hydride, which is generally harmful and toxic for both human and environment. So they are important. Adsorbing acid has a mild reducing ability and is non-toxic and eco-friendly. This work presents a simple and great approach to produce reduced graphene oxide and studies electrochemical properties. The preparation techniques were quite simple, where the dispersed solution was ultrasonicated and stirred at 70 degrees Celsius for 2 hours. The prepared sample was confirmed using FTIR and UV visible spectroscopy. And to study the electrochemical behavior, the prepared sample was coated on flexible fat substrate using spin coating. Cyclic voltammetry study concluded that reduced graphene oxide has high specific capacitance as compared to pristine graphene. Whereas electrochemical impedance spectroscopy study concluded that the charge transfer resistance of reduced graphene oxide and graphene oxide was quite different, which concluded that the reduced graphene oxide shows superior electrochemical behavior as compared to the pristine graphene oxide. Thus, we can conclude that adsorbing acid will be an ideal substitute for hydrogen in the reduction process of graphene oxide. So thank you so much. This was my.
Thank you very much. And the next presenter is Ghosh.
I'm here.
Yes, please.
All right. Thank you, Professor Salesh. So ever since the discovery of tungsten disulfide and molybdenum disulfide nanotubes about 3 decades ago, they have been accepted as functional materials in different labs among researchers. So here in our lab, we are really focusing on the growth mechanisms of this nanotubes. Regarding the tungsten disulfide tubes, we have a precise control on their growth, on their crystallinity, on their structures. So we can produce this around 10 microns and 80 nanometer nanotubes in grams per week. And regarding the molybdenum disulfide nanotubes, we also can produce molybdenum disulfide nanotubes in pure phase and 1D morphology, but currently we are also working in regarding how to improve their crystallinity. So moving ahead, since we are producing the WS2 nanotubes in bulk, we are also looking at their applications. Recently, it was discovered for the first time that WS2 nanotubes in single
This is about it. So I thank you very much for your presentation. And the next presenter is Sridhar.
Yes, I am here.
Mm-hmm.
Thank you.
Please.
Asymmetric 2D or 1D structures such as molybdenum, sulfur, selenium, their nanotube and flakes are very interesting due to the lack of inversion symmetry and time reversal symmetry. But synthesizing this kind of structure is fundamentally difficult because, as you know, it's an entropy-driven reaction, produces a randomized distribution of sulfur and selenium in the lattice at high temperature. But no such 1D nanotube has been produced up to now. But the 2D layer of single layer of molybdenum sulfur selenide is produced by ion implantation by selectively removing the sulfur. But what we are going to present here to synthesize such a asymmetric structure by the misfit layered compounds composing of lanthanum sulfide, tantalum disulfide, we replace the selenium with sulfur, and we see that selenium exclusively go to the tantalum and sulfur goes to the lanthanum. So which says fundamentally we are like outwit the entropy using the chemical affinity in this compound. So we are able to produce many such nanotubes in this work, and recently this work is concluded in our article in PNAS. And for more detail how we do that and how we see the sulfur and selenium exclusively with atomic precision, please visit my poster. Thank you.
Thank you so much.